All right. So this is not week 7. Let me change it actually. Why should I? It's week 6. Easy fix. So yeah, welcome to week 6. So today we're talking about exploring data in general summary and describing what a data set is, something you all have seen in your assignment as well. This one is a shorter lecture. So in general, we have different types of data analysis. Sometimes you need to do qualitative analysis. Essentially, you have a lot of things that you as a human want to explore, want to read and make sense of, understand, because humans have this amazing ability to just make sense of things. So a lot of times you do qualitative analysis of text data or things that are harder for a computer to, even for AI, to make sense of. And this is the part that a lot of human creativity is involved. You can do descriptive or exploratory analysis of quantitative data. This is something that is really useful early on in your storytelling and in your analysis. This is to make sure you want to develop a story, to ask questions from the data, right? To understand what the distributions are, to form questions, to create hunches. And then there's inferential analysis, which more is about hypothesis testing and inferring meaning from data. So that's when you hear we have run an experiment, or it was a randomized data analysis or something, you might run a model, a machine learning model to predict something in the future. So you do analysis that helps you infer something from that data. And I'm sure you've maybe in the summer some of you might take my course. We will do some inferential analysis. But today, for data visualization, we're mostly focusing on visual exploration. So here's a data set, right? And these are things that I'm going to rush by. That's why this is a shorter course, because this is something that everyone should know for with high school. But these are some terms that we've always been using, right? So we have a series of number. The max or the maximum is just the largest number in there. The minimum is the smallest number in there. And the range is the difference between the maximum and the minimum. So can someone calculate the range for me? There you go. 77. There's a meaning in this range, right? It tells us the difference between the maximum and the minimum. It shows us how spread the data is. It's the first description we can give about a data set is that it covers 77 units of something. This data set does not have its unit, so it's just numbers. So it's really meaningless. But it was height, then you could have say, oh, the range is 20 centimeters. So that's how different people are from the minimum to the maximum. Okay. So you can see the range of a population over the years, right? What was the minimum? What was the maximum? You can sort it, you can find it. Usually it's not a problem, these types of analysis. So this is what we talk when we talk about descriptions of a data set. Sorry. Often we're talking about measures of central tendency and measures of dispersion. We're going to talk about central tendency. Let me see something. Yeah. So dispersion is what we talked about range, but there's also variance, there's standard deviation. We might talk about that later today. But when we do summarize a data set based on central tendency, we're talking about the average, we're talking about the median, talk about the mode. These are things that tells us how what happens in most cases with slight different meanings, right? So let's see examples of these. Average is easy, right? You just take the sum of all values in a data set and you calculate it. Okay? That is pretty simple. That's the mean. That's the average. You want to use it a lot. It's useful. You can take averages of things, and it tells you something about people. The average wealth of this class or the average grade tells you something, right? You can compare yourself to the average. And people do that a lot. You say, I'm above average in terms of IQ, even though that's a fallacy. Everyone thinks they're above average, right? So this is something that we see in the real world a lot because it's one of the most universally understood terms. But averages are not always good in terms of descriptors of the data, right? This is the same data set, right, as before, with a mean of 5.5. We just added one extra number of 30. And that one anomaly, which shouldn't really impact things, has increased the mean by a lot, right? Averages are sensitive to outliers because it's just you take a sum of a bunch of numbers and you divide it by the total count. So when you have like this 130 essentially is three of these. So it's just moving things to the right. It's not always good. It's very sensitive. So you need to look at that. You need to make sure that outliers are not skewing your average. You need to see whether your average is a meaningful average. Sometimes they remove outliers because the outliers, for some reason, are outliers and they might not be a representative of what a data set is. Median often is less sensitive to outliers, right? So how, when we calculate the average by taking a sum of numbers, the median is the value, the middle value in a sorted data set, right? Half of the values are greater and half are less than that number. It's pretty useful. You just sort a data set and you say, okay, this is the half point. It's usually, if you add a couple of outliers, it doesn't move the half point as much because you're just counting. You're just saying, okay, what is a number that half of the people are less than? And we've seen this example with like median income, for example. People use median for income because you don't want a billionaire to, even though that moves in, like the median income in Canada is low, even though we probably have a lot of wealthy people. But that shouldn't move the fact that most people are not doing it. But if you take an average of income in the United States, it's probably much higher than what the actual feeling of people is. Okay, so this is how we think about it, right? The average is, this is something that you should always think about, that you shouldn't always take the average. Sometimes you want to take think about whether how you're describing your data. So in general, it depends on how the data is distributed and what's important, right? Both are useful information. If the data has a lot of outliers, you want to use medians. Again, with income, that's something that you want to think about, right? Sometimes they're close to each other. So in this case, you need to look at what's the meaning behind these values and then decide. We have another measure of central tendency, and that's called mode. Mode is just the most frequent value in a data set. If the age of this class is around 22, most people are 22. How old are you? 21, 22 or something close to that, with some older, probably a few younger. The mode is probably around 21 or 22. That's where most of the things happen. So mode is another interesting value that you should think about. And the visualization that we've been using to look at these is called a histogram. It's a very useful tool to explore data set. Essentially, what you do is you split quantitative data into equal sized bins and then count the occurrences of all values within those bins. It's very easy to do. You can do it by hand. We can run like an experiment right now and make one ourselves. So essentially, on the y-axis, you're encoding the counts of the values within each bin. Very simple in terms of how you want to do things. The histogram shows us a lot of things: centrality of the data, whether where it lies the median or the mean, you can guess it. The spread, you can get a sense of where the range is. You can even get a sense of like standard deviation or something. Skewness, which we'll talk about. Outliers, you might talk about if there's one thing in suddenly just out there alone is probably an outlier. And if there's multiple modes, because sometimes the modes are not just one, you can have multiple modes in a data set. This is a histogram, right? And this is a unimodal histogram. This is a unimodal data set. Essentially, this data set is a normal distribution. You might have heard it. It's a normal distribution are these data sets where you have this center and everything just reduces when you go to the right with an interesting like rate. You can look at it and just get a sense of what a normal distribution is. So this is close to a normal distribution. And we'll learn more about it later. And then in these types of unimodal, normally distributed data sets, the mean and the median are very close. But then our data sets you might have data sets that are not normally distributed. So the center is not at the center and things do not fall off when you go right or left. Sometimes your data set is right skewed. Essentially skewed, the mode, the peak is on the left, the skew is on the right. So this is a right skewed data. And this is a left skewed data. Do you remember a left skewed data set that we might have seen before? Anyone? For example, wealth distribution is usually left skewed, right? Yeah, exactly. Or life expectancy. No, life expectancy is also, we have a life expectancy distribution. It's also probably left skewed in different countries. Yeah. But wealth is an important example. It's extremely left skewed because most people are like, there's less. There's in terms of counts, it will not be left skewed, but in terms of amount of wealth, it will be left skewed, right? So it depends on what you're looking at. So if you take count of people who are wealthy, then it will be like this. Let me see if I can draw on the screen. So if you just take count of people, it'll be like this, right? So there's very few billionaires and much less millionaires. Most people are probably just here, right? But then if you want to take the actual wealth distribution of people, then it'll be just very much like a very right skewed data, left skewed data. So with wealth, you will have two different ways of doing things. So how do I clear this? Yeah. Okay. So here you can have the mode on the right, and then when the shape is like this, remember that this is left skewed. When the shape is like this, remember that this is right skewed. So the idea is that you have longer tail on the right side, mean is higher than the median, right? Remember? So the mean is probably around here. The median is probably around here or something. I'm just eyeballing it. I might be wrong, but it looks like this. So because these outliers are shifting the mean to the right. And here's I have an example. Income is right skewed. And again, it's a count of people in terms of income. There's less people with higher income. So this is an example of that, right? You have the distribution of annual household income in the United States, and this is the percent which correlates to the count of households that have this amount of income. And it's interesting, right? So because there's what 15,000 to 19,000, and here is the median, which is close to 50,000. And you see what's interesting, even though the median is close to 50, the mode is even less in the United States. That is important. There's a lot of people. There's 6% of households that make only between $15,000 to $20,000 per year. That's pretty bad. Negatively skewed data sets are like this, if you remember, right? So essentially remember that this is a left skewed data set. Okay. The longer tail is on the left side. Mean is less than median, right? Median is probably here. Mean is probably here. And this is a good something close to all the things that you guys care a lot about. Test scores usually are less skewed. There's probably more people with higher grades and a few people with worse grades, and then the median, the mean is closer to the maximum. So here's an example of test scores. This is how it looks like. Usually test scores look like this. If you take it from 100, usually it's probably like around 80 something if the test is fair, and then you get some drop depending on how good the class is. Data is not always unimodal like the ones we've seen. It can have multiple peaks. Test scores from different classes, or maybe there are sometimes differences between like physical attributes of different genders. Height is an example. If you draw just the height of people in any country, usually you'll get like something like this. And then if you map it by different genders, it'll look like this. So two normal distributions merged together. So that's why you might, when you draw something, you might want to think about what might be some factor that influences this multimodality. These are very simple things to help you think about what's happening in a data set when people show it to you, especially when you see a chart in social media. You can think about a lot of these stuff. In general, some tips about visualization and histograms is you have a choice in picking the bin size, and that is something that you wanna pick properly. If the bin size is small, you might just get too close to the actual data. If it's too big, it might miss some factors, right? Around here, there are some interesting effects that you might not see. Or you might not see that many of the countries are even have less GPUs that are a certain amount. But if you take a bin pretty big, it looks like a lot of countries have good GDPs. Growth domestic product or something. I don't know. That's sometimes my English breaks. Okay, so we have another set of important descriptives that are very similar to median that are called quartiles, or values that divide a dataset into 4 equal parts, helping to summarize the spread and distribution of the data. Each quartile represents 20% of the data. Okay, so that's really important. It gets you're getting more fine grained. This number is important here, 20%. It's useful for understanding how values are spread across a data set. Q1, 20% of the data lower than this number. Median, know it, half of the data is lower than this number. And Q3, 75% of the data is lower than this number. These three are really useful. And using these, we can draw a pretty important statistic visualization. Okay. And that is a box plot. Apologies for this bad image, but essentially a box plot is a visualization that shows you a range, shows you the median, the lower and upper quartiles, and it gives you the middle 50% of what, like 50% of your data lies in, the upper 25, the lower 25. This is a very useful chart to create a visualization. So to think about it again, this is a quartile for GDP distribution. That is the median. So you draw a line, right? This is called a box plot, right? The box is where most 50% of the data is. The median is the middle line. Then you have Q1, this line, 25% of the data lies here. This is Q3, okay? And these little circles are the anomalies. These things that are falling. I think they're more than double this range. They're outside of this. It's called interquartile range. I will confirm it for you. Can you tell me what is the skewness of this data? Is this right skewed or left skewed? Yeah, that is correct. Because you can always try to imagine the histogram, right? So this is like this. The tail is on the right. It's probably something like this. And then, so this is right, good. So besides measures of spread that describe a data, you can, when you usually don't only look at one variable. So far, we've only been looking at one variable, but sometimes you're interested in looking at whether two variables are increasing together. You can think about, hey, is the consumption of chocolate impacting amount of depression in a country? You can say, yeah, the more chocolate people consume, they might be happier. I don't know. It's unlikely that that is true, but it might be, right? You can test it. So you can ask, are two variables increasing together? Are there no relationships between them? Is one of them increasing and the other decreasing? Or whether maybe there's no associations between them. And I gave you the example of chocolate versus happiness because when you say there is a correlation between two things, it does not mean that one is causing the other. Here's something they should, as people who are getting educated in these areas, you should just get this, internalize this for yourself. You cannot, even if it feels obvious that something is causing, let's say, we talked about an example, right? Let's say for a fact that immigration is increasing and housing prices are also increasing, right? Even if these two are increasing together, very much closely increasing together, it does not mean that it is causing it or it is not, right? You just might get a hunch that it might be influencing it, but there might be way too many factors influencing it, right? You need to run a test, you need to be scientific about it, you need to do a lot of things. So when a data set, scatter plots are usually good to look at relationships between two variables, right? Sometimes you see something like this, usually means there's really no associations, or like this. Yeah, you can say they're correlated, right? But it just means that they're increasing together. You just have to be very careful. That's a good question. You just have to be very careful to not assume that when two things are correlated, they are, one is causing the other. And again, you can just think of many examples that helped you, and we can think of example. Does anyone know a good example of correlation does not implying causation? But yes, you can absolutely say they're correlated. Anyone thoughts? We can talk about these later. But in a data set, when you see a line, that means there's like a line that's going like this. It means there's like perfect correlation between them. They're really influencing each other because this is x-axis, this is y-axis. Whenever x is increasing, y is definitely increasing. Sometimes this correlation is strong. It's not a perfect correlation. This usually doesn't exist in real world, right? Sometimes strong correlations exist. It looks like this in a scatter plot. You have a positive correlation. There's something going on. There's just like a general increase, but there's probably other factors influencing this. There's a negative correlation, and there's no correlation. Okay? This is how, when you see data like this, you can read it like this. But again, you shouldn't assume that these two are like causing each other. And we can talk about how you can get a sense of what's causing the other. And in general, correlations, mean, averages are just numbers. And we need to see the data before we can make sense of it. All of these values, they have the exact same means. Even this dinosaur, they have the exact x mean, they have the same exact y mean. standard deviation, everything is exactly the same, but these are all different data sets. So these values that you can get from these data are useful, but it's also important to measure and see what the data looks like to make sense of it. Okay, that's it for today's lecture. I can go to sleep again. This was short. Yeah, I need to get some sleep. Have fun, everyone. I'll see you. Happy Thanksgiving. It always bugs me because I used to live in the US, so it's unnatural for me to say Happy Thanksgiving now, but Happy Thanksgiving. Have fun. Take care, and we'll see each other soon.